Okay, so welcome to this special session. We are very happy to welcome Gannon, who will talk about convoluted dynamics.
Thank you. Thanks for inviting me. So yeah, I'm going to talk about dynamics, and this is all joint work with Artem. So okay, so what are we actually talking about? So in the context of NIP theories, certain families of keys or measures form nice semigroups. Okay? And under this operation called the definable convolution operation, they're nice semigroups. And so what can you do when you have a nice semigroup? Well, you can try to figure out what the minimal ideals and the ideal subgroups are. So in this talk, we're going to discuss exactly what they are. And we'll see that somehow the ideal subgroups are always kind of trivial. You don't really care about it. But computing the minimal ideals is actually harder. So let's start by talking about types, or I guess notation. So throughout this talk, T will be a complete first order theory spanning a group, the language of groups. And I'm going to let this math cal G, this is going to denote a monster model of T. And then I'm going to use regular G to denote a small elementary subgroup. I'm going to use this notation. I don't know how to say this in words. This notation is going to denote the space of types, global types, which are automorphism invariant over G. And then if I change the I and V with an FS, this is going to denote the space of global types, which are finally satisfiable over G. And sometimes I want to discuss both spaces at the same time. And to do this, I'm going to just write a little dagger here. So the dagger means that it's either one of these two. Is that okay? Yeah. So both of these spaces, right, the space of global types that are finally satisfiable over G and the space of global invariant types form natural semigroups with this product that's written as a little star. This operation is defined as follows, right? So if I let P and Q be in the same space and I choose any formula, then this formula is going to be inside P star Q if and only if the product formula is in the Morley product of Px star Qy. This defines a semigroup operation on the space of types. And it's important to notice that this semigroup operation is a continuous map, right? And by continuous map, I mean it's right continuous. If I put something on the right, well, it's left continuous. And that means if I put something on the right, the map is continuous. It's a little confusing going back and forth between left and right. But if I put any fixed type on the right-hand side, then this map is continuous. Oh, sorry. Question. You first realize Q, then P. Yeah. So the Q is being realized first, right? So the thing that I'm realizing first, and then it's a continuous map. Yeah. And this is all types, and all this generalizes nicely to the setting of measures, but So to actually talk about the minimal left ideal and the ideal subgroup, I have to define what those are. We'll recall some things from semigroup theory. So if I have X is a compact Hausdorff space and X with a product is a semigroup, so I have some semigroup structure on the compact Hausdorff space, then a subset I of X is called a left ideal, right? If I is closed, and if I multiply by X on the left, then it's a subset of I. Moreover, we say that I is a minimal left ideal if I is a left ideal and does not properly contain any other left ideal. Did I say that? Yeah, any other left ideal. So we say that this semigroup is left continuous if for every P in X, the map, right, multiplying by P on the right is continuous. So that's what means to be left continuous. It means that multiplying on the right is continuous. That's great terminology, right? And then finally, so we need to know what an idempotent is. So if I have some elements in X, we say that mu is idempotent if when I multiply it against itself, I get itself. Yeah. It's 5 of 1, yeah. That's what it means, yeah.
You just have to check it. You have to check it one more time.
Tech what one more time? This is the last slide. So. Okay, so the excuse me. So the minimal ideals of left continuous compact Hausdorff semigroups, right, emit a strong decomposition theorem. And so, okay, all the semigroups that we'll be discussing today will be this type of semigroup. And so the strong decomposition theorem, we can use it. So what does this decomposition theorem say? So suppose that I start off with a left continuous compact Hausdorff semigroup. Then, first of all, X contains a minimal left ideal, I. And first of all, I can find an element in I that's an idempotent. For each idempotent, if I multiply on the left against my minimal ideal, I get a group. And moreover, this group is unique. Okay, in what sense? So if I have any other minimal ideal J and some idempotent in J, then this group that I get here is going to be abstractly isomorphic to U times I. Right? So it's the same group. And we define the ideal subgroup of our semigroup to be the isomorphism type of this group that we have found. Okay. Any questions about this? No? Okay. And what's the decomposition theorem? Well, I is going to be the disjoint union of these ideal subgroups. So more explicitly, if I let I of I be the collection of idempotents in I, then I can write I as literally the disjoint union under these sets. Right? So if I have a little picture, here's X, here's I. Right? I have one idempotent in each of these chunks. So this is maybe U prime. Right? And this is what it looks like. This is the decomposition theorem. And each one of these is groups. And, okay, I should say, moreover, the idempotent inside each component is the identity of the group.
When you say it's an abstract group, you mean without the topology?
Without the topology, yeah. As an abstract group, yes.
It's not a topology, it's not a homomorphism.
No, it's not. No, that will become important. Yeah. Okay, so in the type case, okay, we know what some of these ideal groups are and some of the minimal ideals are, right? So both these two semigroups, right, fit into the framework from the previous slide. So in general, you can, okay, in general, it's hard to compute minimal left ideals and ideal subgroups, right? But okay, here are some examples. Okay, so this was the what is it, Ellis group conjecture, right? So at least in the definably immutable case, right? So assume that T is definably immutable in NIP, right? Then if I take a minimal ideal and an idempotent in there, then the ideal subgroup is going to be isomorphic to G mod G0. And you might think, oh, why doesn't this, maybe this works for all NIP groups, but it doesn't, right? So, okay, I have a little asterisk here because technically it's in a slightly different context, but
I mean, this U star I, there's a natural homomorphism to G mod G0. Two onto it, and it turns out it's not. So this, we have U star I.
yeah.
There's always a natural homomorphism to G mod G0.
Uh-huh.
And in this particular case, it's an isomorphism.
In this particular case, yeah, when you're defining what you mean.
So the natural, there's more. The natural homomorphism
Uh-huh.
is an isomorphism.
Okay,
It's not just an abstract isomorphism.
okay,
You know what I mean?
sure.
Again, it's only in an abstract group, like homomorphism now, which you want to 0, 0.
No, but there's a natural homomorphism.
Is it a topological homomorphism?
No, it shouldn't be.
No. Well, in fact, it turns out, yes, but there's more stuff to say.
I don't think so.
There is more stuff to say.
Yeah, but what do you mean that it is?
It turns out that U star I is, with a certain topology, is a compact Hausdorff group. With this, what's it called? Topology, it's called, what's it called? The topology, you know, the topology called, what's it called, or something topology?
Yeah, something topology.
What?
I know what you mean.
I know it.
The something topology.
Yeah,
It's the start topology, something.
Okay,
taking the topology from G1, G0, 0.
What? No, there's another topology given by Ellis.
well, I just want to say that,
It's called delta topology. Pardon? Christoph, what is that? Sorry. What, Christoph, what's
Yes.
what's the topology on U star I? What do we call it?
Okay, it is called tau topology.
Sorry, the tau topology.
Tau
The tau-
topology. It is quasi-compact. It is compact, but not necessarily Hausdorff. And
In
the
this
group
ca-
operation is separately continuous.
Yeah, so in this particular case, it's actually Hausdorff, and this is an isomorphism of. So in the amenable whatever, you actually get in some
With the
canonical
other
way.
topologies,
It's
yes.
even the isomorphism of topological groups.
Yes.
Yeah. Okay. Sorry.
Great.
So you mean that all this U times U star I is, I mean, they carry the same topological group structure, right? I mean, you
Yes.
said that they are isomorphic as groups, but with this topology, they are isomorphic as topological groups, right?
Yes.
Okay.
Can we continue? Yeah. Okay, great. So, right, so it's not always true that, okay, this ideal subgroup that you get is isomorphic to G mod D00, right? Okay, and here's a counterexample is SL2R, right? In SL2R, you get that the ideal subgroup is isomorphic to G mod 2Z, or sorry, Z mod 2Z, and G mod G00 is a single thing. Yes? But it's slightly different context because I'm talking about, right, this is computed inside, right, the real field. Whereas I'm. Why did it different? Well, okay. I mean, formally, right? I mean, my setting, I'm just fixing a theory that's extending a group, right? Instead of a group definable in a theory, but it's the same. All the theorems transfer.
What if you replace FS by environment?
Yeah, it's a different story.
This is
One is global. Also something upstairs about, isn't there? About the extended defining.
it's the same as finally satisfiable.
Yeah, sorry.
Yeah.
But what if you take invariant types?
I don't know computations about invariant types in either of these settings. Okay. Okay, so kind of in the same way, Keyser measures. Okay, well, I should tell you what Keyser measures are first, right? So a Keyser measure is a finally additive probability measure on Lx of G, right? And all the formulas with free variable x, right? With parameters anywhere. We denote the space of Keyser measures as Mx of G. Okay. So, okay, I'm going to have kind of the same type of notation. So this MXM of GG denotes the collection of measures, right? So global measures, which are automorphism invariant over G. And when I replace I and V with FS, right, this is going to be the measures which are finally satisfiable over G. Is this okay? Or should I say more about this definition? Is this fine? Okay. So, okay, if T is an IP, then both these spaces are naturally left continuous compact Hausdorff groups, right? Just like the types. So from this observation, right, one can ask the following two questions.
Kyle?
Yes.
How to multiply measure?
We'll do next slide. Yeah. So
Actually,
from this observation, so one can ask the following questions, right? So what are the ideal subgroups of these semigroups, and what are the minimal left ideals? What do they look like? Right? We have nice semigroups, and now we ask, okay, what are these objects? So first we need to discuss, okay, what do I mean when I say Keyser measures as a semigroup? Okay, so there's a definable convolution operation. So if I let mu and nu be global measures in one of these two spaces, we define the convolution product denoted mu times nu, right, to be the unique measure in the same space, such that for any formula we have that. So the convolution product on the formula is equal to the Morley product on the product formula. Okay, and this is fine unless you want to actually compute. So how do you actually compute this? Well, you have to take an integral. So this is, okay, let's be kind of clear, right? Okay, well, first, right, what are you doing? You're integrating kind of the fiber function over the other measure. But okay, where G is a small elementary submodel of G containing our original model and parameters from our formula. This function here maps from this type space to 0, 1 by just asking what the measure is on a particular type. And by invariance, this is going to be well defined. Sorry? Because I need parameters, right? Parameters might not be in G. So that's why I need G prime.
Phi isn't the
Phi prime.
Phi prime is like the bipartite.
Oh, yeah, phi prime is special. Okay. So phi prime is for the special. The special. Yeah. Yeah, it just means that you're multiplying them for phi. Okay. So this is fine. And then, okay, what is nu G? Well, nu G is the unique regular Borel probability measure extending, okay, when I change the free variable from X to Y, right? And then extend it to this type space. Okay. And this is the Morley product. Okay, I mean, this is how you compute the Morley product of this.
Wait, you said nu G prime is the unique measure extent.
Sorry?
Rho G prime on both sides.
What's on both sides?
G prime.
G prime.
Bullet 3. Bullet 3. So G prime is both. The left hand of the.
Well, this needs to be a measure in the space, right?
Nu is equal to G prime. The unique regular Borel extending nu is equal to G prime.
Yeah. So this, right, which is written here, is okay. I'm thinking about this being a Kiesler measure, and I'm thinking about, okay, you're right. I've called them the same thing, but this is like the regular Borel probability measure, and this is okay. When I have the little y here, that's the only difference. But this is I'm thinking of as the Kiesler measure. Yeah. Okay. Thank you. Okay. So how do you actually compute? Well, okay. Here are some examples of computations. So what do? So suppose that I have A1 through AN and B that are all in G, right? Then the convolution product on realized points is just going to be the product of, the Dirac measure that concentrates on the product of the points. If I have some tuple, right, and I want to take the convolution product between the average measure and some other measure, well, then it's just averaging the measure of the translations of the formula. Do we know what I mean when I say average measure? Is that okay? I don't need to say anything. Okay. So average of A bar on a formula phi of X, right, is just going to be the number of indices such that phi of AI is true divided by N. Okay. So just the average, just averaging. Okay. And then, okay, maybe a non-trivial example is if you let T be, okay, the theory of the reals, right? And G is just the copy of the reals. I can build a measure, right? Which is going to be the unique measure over the whole space. Where what do? The measure of a single formula is going to be the real points in the interval 0, 1, such that G models phi of A. And this is well defined by ominimality. Okay, so it's just what is it really? It's just the Lebesgue measure sitting on inside the model. Right, restricted to the interval 0, 1, right? Where L is the usual Lebesgue measure on the reals. Then, if you sit down and try to compute, you'll show that the convolution product of x less than 1 is equal to a half, and the convolution product of x is less than 2 is equal to 1. Okay? So if you're bored during the talk and you want to try to figure out the convolution product, well, you can try to do that. Okay. So in the last paper that me and Artem have, we proved some stuff about these spaces. So if suppose that T is an IP, okay, then this convolution product is well defined. Definable convolution extends the product in types, right? So if I take the Dirac measure concentrating on a type, then it's the product of the Dirac measures, or the convolution product of the Dirac measures. Okay? So, and then the last two facts really use an IP. So the convolution product is left continuous, right? So if I choose any measure here, then this map is a continuous map. And this uses kind of the language of smooth extensions. And then finally, we will also prove that, okay, definable convolution is associative.
So Kyle, but when you are saying that it is well defined, so what is the point? What is to be checked to show
well, I mean, in the sense that if you take, okay, two finally satisfiable ones, if you take the convolution product, it's finally satisfiable. Right?
Okay.
And you take two invariant ones and the product is invariant. Yeah.
Okay. Yeah.
But the fact that you can detect it for the continuity and for that.
Yeah, for invariant ones, even to take the product, yes. Yeah. So that's also necessary, right? NIP is kind of throughout everything, you need this. Yeah.
But if you,
Right? To have compact semigroups, you need somehow you
why do
need
you call it
NIP.
definable convolution instead of just convolution?
I could just call it convolution too. Yeah. That's fine. I mean, it's
Other than the convolution itself is definable. Axon.
no, but it's convolution from definable objects, right? To okay. I mean,
Can I ask a question then? So if G is, if plain G were countable, then could you, I mean, you need NIP as much, or could you work with Borel definable and so this it could be NIP?
Over a countable model, it's true for more than parallel.
I don't know how I even proved that this map is continuous if I didn't have.
Okay, except removing, but just getting that it's well defined.
But I think we use this to get us. Sorry, you're just asking if it's well defined. Yeah.
Well defined associative semigroup. If you just did Borel definable over a countable model.
I don't know if it's going to be associative. Because we use a lot of, I mean, you use a lot of like generic stability type things.
It's not just coming from associativity of the Morley product.
No. That's like a step in a bunch of other steps.
I see. Okay.
Yeah. No, it's more difficult than that. Yeah. Yeah. So I don't know. Okay. So we conclude, right, that if T is NIP, then both these spaces, right, the space of invariant measures and the space of finally satisfiable measures form left continuous compact Hausdorff semigroups. These, okay. There should be a better name for this. Is there a better name for this? Does anyone know? And so it makes sense to talk about, okay, they're minimal left ideals and they're ideal subgroups. Yeah. Okay. So, okay. Let's do the easy cases first, right? So suppose that T is NIP, right? Then the ideal subgroup of any of these spaces is always trivial. There's no interesting ideal subgroups, right? So if I is a minimal ideal in this space, there should be a dagger here, excuse me, and mu is an idempotent in I, then okay, it's going to, the ideal subgroup is going to be a single point. Okay, so that's not interesting. The ideal subgroups are not interesting. If T is definably amenable, and I is a minimal ideal in this space of finally satisfiable measures, then it's equal to a single point.
Sorry, dagger means what is dagger?
Dagger's either inv or fs.
So this isn't it not like the case of types?
It's not like the case of types at all, no.
But there is a map from the types. It's type, right?
So these are invariant measures, right? We're talking about invariant measures.
Yeah.
Can you maybe explain why?
Yeah, I will.
Okay.
Yeah, so, okay. So if T is definably amenable, right, then the minimal ideal is a single point. Okay, but okay, this is important that you're in the space of finally satisfiable measures. And what is this equal to? Well, it's just equal to a single measure that is left G invariant. So
the point being here that you get these G invariant measures, but not the particular G invariant types.
yes,
That's the point.
that's more or less the
When you
point.
pass the measures, you can get when you pass the measures, you can get G invariant objects, but they need to be G invariant types. That's the point.
Yeah.
So it's like working in a connected group.
Yeah. And if, okay, T is definably amenable and I is a minimal ideal of the space of invariant measures, then it's going to be equal, there's a unique minimal ideal and it's equal to the global measures that are right G invariant. So you move from left G invariant to right G invariant when you go up. Okay. Yes, you do get that all of these are just unions of idempotents. Yes. Yes. Okay, so the proof of one is a slight variation of this proof that there does not exist any non-trivial compact convex groups. And the proofs of 2 and 3, okay, are straightforward computation arguments. Right? I mean, this is just kind of a straightforward thing to do. I mean, you start off with a left G invariant measure, and then you just compute what happens when you take the convolution product. So okay, we'll prove one because it's more interesting. The other ones are just computations. Okay, so let's do it. We want to show that if I is so let I be a minimal ideal of this space, right? It suffices to find some idempotent such that mu times I is isomorphic to a single point, right? Okay. So what do? Well, the first thing that I need to prove is that this idempotent, or excuse me, this minimal ideal is going to be a compact convex set. So that's the first step. This is not too hard. It follows from bilinearity of integration. But okay, so we first do this. Then, okay.
Wait, what do you mean by convex?
So, right, formally, I is sitting inside the space of measures, and this is sitting inside of a, what's it called? A vector space, right? So I can talk about what it means to be convex. Yeah. So, so I is going to be a compact convex set. So there exists an extreme point, right? It's by Crane-Millman. I can find some extreme points inside my set. Okay. Okay. Then by this picture, right? There's going to be some idempotent, right? So one of the ideal groups is going to contain my extreme point. Right? Okay. And then by some algebra, you can show that mu is going to be an extreme point inside this space. Okay.
What is it that we?
So an extreme point is a point that cannot be written as a convex combination of other points inside the set. Yeah. So that's all I'm saying, is that when I say extreme point, that's all I mean. Okay. So the point is that you're going to have this idempotent, right? That's going to be the identity of this group. That's an extreme point. Yeah. Okay. And now suppose that you have two elements, two distinct elements inside your group. Right? Since this group is convex, right? We have. Sorry. Somebody say something? Am I hearing stuff? So okay. So we have that alpha is equal to eta 1 plus eta 2 over 2 is also in my group, right? Oh, I guess yeah. You need to prove that u times I is convex, but this is not. Excuse me, this should be mu. Mu times I is convex, but this is not difficult, right? Then, okay, mu is going to be my identity in my group, so I can write it as alpha inverse times alpha, but then I can write this as a linear combination. Right?
Wait, the vector space operation it commutes with the.
Yeah, it works nicely. Yeah, with sums. Yeah, yes. So okay, I've now written mu as a linear combination of two measures, right? So that implies that these two measures have to be the same, right? Because it's an extreme point, right? So then I get that alpha inverse times eta 1 is equal to alpha inverse times eta 2. But now I'm done, right? Because I'm in a group, and so eta 1 has to equal eta 2. Okay. That's it, yeah. So essentially, right, I mean, the theorem should be if you have just a bounded, right? I mean, you use compactness just to get the points, and then you're done. Yeah, that's it. That's all you do. Yeah. Yes. Okay, so as a corollary, right, every element of I is going to be an idempotent. Right? So why is this true? Well, if I just look at what do I want to write? So I know that I have I is equal to the disjoint union of the idempotents, right, times mu, let's say mu times I, right? But each one of these is a single point. So this is going to be the disjoint union of mu and I of mu, right? And each one of these mu's is an idempotent. Right? That's by definition. So okay, so we have these big objects that are just collections of idempotents. Okay? And we didn't use definable amenability, we used nothing. Okay. So let's look at an example. So let's consider the reals, right? Just in the language of plus, less than, and 0, right? So what is it? Divisible order of Ewing groups. And I'm just going to let P and Q be the unique types extending, okay, I'm greater than everyone, and I'm less than everyone. Right? So okay, what are going to be the minimal ideals here? So if I let P and Q be the unique global co-heirs, right, of P and Q over R, right, so the cuts right above the reals and right below the reals, then the minimal left ideals in this space are just the single types, P and Q. Okay.
Are they something that you have to prove?
Well, it's obvious from the theorem that I stated, right? From here, you have that.
You're looking at the measure.
Yeah. Sorry. Delta P and delta Q. Did I not write delta P and delta Q? Yeah, sorry. These should be delta P and delta Q, right? Yes. Thank you. So these are going to be the left minimal ideals in this space, right? But in my other space, right, if I let P tilde and Q tilde be the unique global definable extensions of P and Q, right, then the unique minimal ideal is going to be this set. Okay, it's just convex combinations of the two types, right? The Dirac measures on the two types. Okay? So this is what you get in the other space. Okay. Okay, so what can we say when we are not in the definable amenable context? So, what do you mean? Well, in the first theorem we were some of the time, right? Yeah. So I want to say something about minimal ideals, right, outside the definable amenable context. Okay. So what can we say? Well, there's kind of an easy fact that if T is an IP and not definably amenable, right, then and I is a minimal left ideal inside the space, right, then I has infinitely many extreme points. So this is kind of an easy fact. Right? So how do you? Infinitely many, yeah, infinitely many extreme points. Right? So it's going to be, okay, it can't be like a triangle, right? So there's only 3 extreme points. Yeah.
Okay. So who proved this? What this fact?
We proved this.
So this is something new, or?
Yeah, this is new. This is all new.
Okay, I see. But usually for me, fact is something like known. Okay, but I see. Okay.
Oh no. This is fact is proved, but it's short, so it's a fact.
Should we try to say new fact?
New fact, yeah. New fact. Yeah. Okay. So how do we prove this, right? So suppose not, right? Then the extreme points are finite, right? I have finitely many extreme points, right? And it's easy to check that for any g inside little g, if I look at this map, right, it maps extreme points to extreme points, and it's a bijection. Okay. This is what I claim. Then I just average these measures, and this witnesses definable amenability for g, and so you're done. It's a contradiction. So okay, so the spaces in the not definably amenable case are going to be more complicated. Yeah. Okay. No. Unknown. Let me think. I have a minimal idea. Yeah, I don't know.
So where do you use the fact of extreme points?
To get that G maps from extreme points to extreme points. Yeah, get that this action is a bijection. Yeah, right. And then because of that, right, then this measure is going to be fixed by acting by G, right? And so it breaks definable amenability. Okay, so right, somehow the way that we described how we got minimal ideals is okay. It's a little unsatisfying because you just kind of say it, right? The descriptive answer. And okay, we need to know how to construct minimal ideals so that we can solve some stuff outside the definable amenable case. So now we're going to give a method for constructing minimal left ideals, right, in these spaces, right, using a minimal left ideal in this small space. Okay. So how do you do this? Well, okay, so if I is a minimal left ideal inside this space of types, right, we let just M of I be the collection of measures whose support is contained inside I. So these are going to be all the keys or measures whose support is contained inside the set I. You can do this for any set. It works better for closed sets, but Okay.
I is closed.
In this case, yeah, I is closed. Yeah. I was just saying you could replace I with any subset of types, right? And you can make this definition. Okay. And if, say, this is another fact, but it's easy, so I call it new fact. Sorry. So if I is a left ideal in the space, right, then the space of measures, there's no X here, excuse me, is a left ideal inside this space of measures. It's not going to be minimal. So minimality of ideals is not transferred. Right? So an easy way to see this is if you look at the circle, right? Look at finally satisfiable types over the circle. The minimal ideal here, okay, is going to contain all types that are finally satisfiable over S1. And the minimal ideal upstairs is going to be a single measure. So the minimality doesn't work. It doesn't transfer. But okay. So this is how you get an ideal upstairs from an ideal downstairs. Okay, types are downstairs, measures are upstairs. Since right now. Sorry. Right? Okay, so how do you actually get a minimal ideal? So suppose that I is going to be a collection of types, right? Is minimal ideal in the space of types. And there exists an idempotent in I such that the induced topology on this space is compact. Okay. So the is a compact group, excuse me, right? So it's not the tau topology, it's just from the original group, from the original semigroup, excuse me. Okay. Then I'm going to let H mu I, excuse me, H ui be the normalized Haar measure, right, on this group. And I'm going to let mu ui be the Kieser measure that you get from the Haar measure. Right? This gives you a Kieser measure on the space, and it comes from the Haar measure. Right? Then, if I look at this convolution product between this space of type, excuse me, this space of measures and this measure, this is a minimal left ideal inside this space. Okay. So I've written it as the space of measures which concentrate on a minimal ideal times a Haar measure living on an ideal group.
Sorry, if the induced topology is a compact group, doesn't that mean it's closed? The U star got to be closed.
U star have,
Induced topology is compact.
yeah.
U star the topology induced from.
Yes, it implies, yes.
This implies that U star I is closed,
U star I is closed.
right?
U star,
Isn't that something fishy about this thing?
U star I is closed.
Yes,
Well,
that's
okay.
true.
What's mu star I?
U star I. U star I, your Alice thing,
Yeah.
is going to be closed. Isn't that something? Isn't that impossible?
Well, it can happen in invariant types, and it can happen with
U star I is
if you're
closed.
finite.
U star I closed. U star
Right?
I is- What? Yes, yes.
So, okay. Here's two examples, right? So if you let I be a minimal ideal inside LX, okay, inside this space where, right, it's not just finally satisfiable, you're also thinking about invariant types, right? So if every element in I is definable, then this is going to be a compact group. And then the other case is if the ideal group is finite, then this is a compact group, right? So what is the example of this case? Well, okay, if I look at invariant types over the integers, right, in the language with ordering, then I'm in the first case, right? This is going to be a compact group. It's going to be Z hat.
Kai, is in this theorem somehow in the background this other Vendel theorem hidden? You know, the one when you say that idempotent, if you have something is idempotent if the restriction to the support of this guy is exactly Haar measure, right? If you have this restriction, there was
Yeah, this is not part of that. No, this is different.
no. Okay, thanks.
That's not hidden in the background. No. Right? If every element of I is definable, then you get a compact group. And this is happening in the case of invariant types over the integers. Right? And then the other case that you have is SO2R, but that's because it's finite. Right? That's it.
So, Kyle, but could you say what you are saying in this example? Because I can't see it on my screen. It is covered
Oh, you
by some
can't,
black.
is it too low? Right here? Wait, what can't you see?
I can't see this example at all. This last.
It's at the
line.
bottom of the screen.
Yeah, I know. But so what it says, this example?
Yeah, so the examples that live inside this case, right? So especially case one, so if every element in I is definable, then this is a compact group. When does that happen? Well, if I look at the space of types that are invariant over the integers, right? In the language of plus, less than, and 1, right? This is a definably immutable group, but okay, this is going to be your space of, sorry, so you actually get a compact group, right, with the induced topology. It's going to be Z hat. That's what I'm saying.
Okay.
I'm saying that this theorem is not null, right?
You
There's
should be
things that
able to see it
satisfy.
on the other screen on the model theory participant. Can you?
Oh, yes,
Christoph?
yes. I can make it larger. Yes, and then I see.
Right.
Okay.
Is it okay? Or can I move on, or should I stay for a second?
Yes, please
No.
go. Yes, go on.
Okay. Good. Okay. So let's prove it. So suppose that I is a minimal ideal inside the space of types, right? And there exists an idempotent I such that this is actually a compact group, the induced topology, right? And I want to show that this, right, product is going to be a minimal ideal inside this space. Okay? So how do I go ahead and do that? Well, okay. The first thing you need to check is that the space of measures that concentrate on I, right, is a left ideal of this, which I already said is true in NIP. Right? Second, right, then there's going to exist some L, which is going to be auxiliary. It's going to be a subset of the space of measures, right? This ideal, such that L is a minimal left ideal, right, in the whole space. Right? So the first thing to do is to show that for every element in I, right, you show that this product of the Haar measure and delta P is equal to mu, is equal to the Haar measure, right? And what's the picture? I mean, somehow what's going on? Well, okay. So here's my minimal ideal. It's broken up into these spaces. And what's happening if I act by delta P? Well, it's just permuting each piece. Right? That's kind of the picture of what's going on. So it's going to fix the Haar measure. Okay, so using 3, you can do this trick, right, where you extend from types to measures. This is a usual NIP trick. Okay. And so from there, you get that, sorry, this should be mu sub ui, the Haar measure times the whole minimal ideal is going to be equal to itself. And so U has to be an L, right? Since L is a minimal ideal. Is it clear? Yeah. Okay. And then by semigroup theory, you get that the space of measures times mu, these mu should be U sub i's, right? The Haar measure is equal to L. You get the minimal ideal. And then, okay, you just compute, right? So L is going to be a subset of this, right? L times mu, the Haar measure, which is going to be a subset of this, which is going to be a subset of this, which equals L. So the statement follows. And getting this is actually a little bit, you need to know that every element is an idempotent. So that corollary I said earlier, to actually prove this first part, you need that. But okay. This is minimal ideal. But okay? Okay. Okay, so if you assume more, and really this is just going to be, I mean, you should assume that the real assumption should just be that your ideal group is finite, but you can write it kind of crazily. But if you assume more, you can actually parameterize the minimal ideal by space of measures. Okay. So how does it work? So suppose that I have a minimal ideal inside the space of types, right, with the following properties. Okay? So for any idempotent, you have that mu times I is compact. Second of all, you have all these maps that are continuous. So if I take anything in the minimal ideal and I multiply on the right, you have that it's continuous. Okay. Usually continuity is on, when I multiply on the left, it's continuous. Usually continuity is on the right, right? But here I need to say that it's also on the left. And then finally, you need to assume that the quotient is Hausdorff. So what is the quotient of I? Well, my quotient is taking in, saying that two things are in the same equivalence class, right? If and only if they live inside the same group. Okay? So this is my quotient. And so, okay, if you have all these conditions, then your minimal ideal is going to be isomorphic. There's a linear homeomorphism from this space to this space, right? Where this is the space of regular Borel measures on the quotient. So, okay, the only example I have is SL2R. Okay, other than some simple examples, is there's a linear homeomorphism between these two spaces. So it's like parametrized. No. This is just asking what does this space look like, right? So it looks like a space of measures over this quotient.
What about SL2QP?
I don't know. What is the ideal group in SL2QP?
We did it.
Well, what is it? Is it finite?
We did it. It's there. No, it's not finite.
Okay, well, then I don't know. Well, right. I mean, I need the only thing that I know that works for this is if you're finite, because I need this third condition that says that the quotient is Hausdorff. But okay, if you have this, right? Okay, in SL2R, you know what it is. So you actually get this. You know what the minimal ideal looks like. Yeah. Okay. And that's it. Thank you.
The one. Yeah, I said pointing out the one.
So are there any questions?
What about these bias that you said? You don't know anything?
I don't know.
What about?
What about invariant types? What do you know about like?
I don't know much about invariant types. What the minimal ideals or ideal subgroups are for invariant types. You should have some right. You have a map from invariant types to finitely satisfiable types inside NIP theories, but I don't know how that works. Yeah, I don't know for invariant types. I only know like a couple computed examples, like for the integers.
Anyway, for SL2QP,
Yeah.
For SL2 cube, there's a computation of the ideal of all these ideal group business, and
Yeah.
it's infinite. It's not finite. It's infinite.
Right.
And so,
that poses problems. Yeah.
but your assumption don't give it doesn't fit into the last.
It doesn't fit into the last one where you parameterize the.
Why?
Oh, it's unclear if it does. Sorry, you're right. It's unclear if it does.
Okay. Okay. Thank you.
Okay, so I think we can thank Kyle again.
Thanks.